Good evening to all our viewers. This, I believe, is our 40th webinar that we've been doing since April 2020. And we have an interesting topic today. In 1937, I believe it was, a 26-year-old engineer in Wheaton, Illinois, actually built the first radio telescope. But that was 7,000 miles away. In India, a young man who studied at Stanford and who actually, his wife actually stopped him from meeting Hewlett, so that Mr. Hewlett could not offer him a job because they had kind of decided to move back to India from Stanford. And I think Hewlett was wondering, who's this crazy young man who's giving up a job in Stanford to go back to India? So, so that gentleman came into Bombay and joined TIFR. His name is the legendary Professor Govind Swaroop. He passed away, unfortunately, almost to the day a year ago, September 7th, 2020, was when he passed away. And he was instrumental in building, the first few radio telescopes. In fact, building the entire radio telescope program in the country, starting with the first radio telescope outside Bombay at Kalyan. And then in Ooty between 1964 and 1966, I think they built the Ooty radio telescope. And after that, the GMRT, the Giant Meter Wave Radio Telescope, is probably history in a big way for us, which has 30 fully steerable, an array of 30 fully steerable telescopes, 45-meter diameter each. So it's a big operation out there. We couldn't have found anyone better to chronicle this inspiring journey. It's a pleasure to introduce Hari Pulakkat, a journalist, a winner of the Indira Gandhi Prize for the Popularization of Science. And Hari has recently published a book called Space, Life, Matter, where he walks the reader through several such inspiring journeys post-independent India in the journey of science. So he's very painstaking. I've read the book. It's a lot of detail. It's an exciting story. I could not put it down. I just had to finish it. So it's a great read. So I will hand over to him, but let me just walk through a few of our house rules. I'm sure there will be lots of questions. So please put them in the Q&A box. Do not put them in the chat box, because the chat box is not being monitored for questions. Sushila, my colleague Sushila Venkatraman, and I will be moderating this session. And, we'll allow Hari to speak for 45 to 50 minutes and then start taking all the questions. And at the end, Sushila will summarize the key takeaways from today's webinar. So without any further delay, Hari, over to you.
So thank you, Ashok, and thank you, Sushila, for giving this opportunity. My book contains a lot of personalities in several aspects of science in India. And one of the most memorable experiences for me was to write and learn and write about what Govind Swaroop did in India. And I hope I can communicate some of that excitement today. I have some slides. I'll start sharing them. Okay, so I start with a map here of the British Empire in 1920. There are more than 30 countries current, in this map. And if you leave out Canada and Australia, which are countries made of primarily of European immigrants, India stands sort of unique in one respect, because none of the other countries had science to any significant extent at the time of independence, their independence. So in 1947, India was probably the only country which had a significant scientific program. And if you look at in 1947, what we did, so we had C.V. Raman, already a Nobel Prize winner in 1930. In fact, he was the second Nobel Prize winner from the former British colonies, and the first one was in Canada, and not in Australia. Meghnad Saha had discovered the Saha ionization equation. S.N. Bose developed Bose-Einstein statistics, also work done in the 20s. So something had been happening in India already when India got independence. So these were the institutions, primary institutions in India in 1947. So Indian Institute of Science started early in the 20th century. Tata Institute of Fundamental Research started in the 1940s. Universities in Bombay, Allahabad, Madras, and Calcutta were old, much older than that. And you had Banaras Hindu University also, and a few others. So Govind Swaroop was born in 1929 in Thakurdwara in Uttar Pradesh at the foothills of the Himalayas. I think about 50 to 60 kilometers from Moradabad. So he did his MSc in physics from Allahabad University, then went to Australia for 2 years on a fellowship and worked with Joseph Posse, radio astronomer. And then he came back, he built some, about 30 antennas at that, in Australia during this 2 years. And Australia donated those antennas to him. He wanted to bring them. So unfortunately, Indian government wanted them to bear the cost of shipping also, which Australia was not willing to do at that time. So Swaroop waited for some time, and then he left for the US, and he worked in Harvard for some time, went to Stanford, did a PhD, and then came back to join TIFR in April 1963. In fact, the TIFR wanted him to join on April 1st, and he refused to join on April Fool's Day. So this was the situation in radio astronomy at that time. So Carl Jansky built the first radio telescope in 1931. It was not quite a radio telescope. He just put some antenna on a platform with some tires, car tires, and then he got signals from the center of the galaxy, which was big news in 1931. But unfortunately, Jansky could not continue this work because he was working in Bell Labs. Nobody in Bell Labs was interested in funding this program because they were interested in transatlantic communication. And Jansky's job was to figure out what would interfere with that communication. So then Gro Treber was a 26-year-old engineer, picked up from there and built a dish there, which confirmed Jansky's discovery. And then there's Purcell and Evan discovers the hydrogen spectral line in 1951. These spectral lines at 21 centimeters is because of synchrotron radiation from neutral hydrogen atoms. And contain a lot of information and became a big tool in astronomy later. So by 1960, when Swaroop was in TIFR, several hundred radio galaxies have been discovered. And temperature of solar corona and Venus measured, and quite a few other things. So radio astronomy was a very well-developed field already when he came back. So these were the telescopes around the world at that time, the major ones, radio telescopes. The Dwingelow telescope was 25 meters in diameter. The Jodrell Observatory was 76 meters in diameter. The Parkes Radio Telescope, 64 meters. Green Bank Observatory, which was a parabolic dish for 90 meters in one direction, in the diameter. So there is an interesting film about the Parkes Radio Telescope called The Dish, made in 2002. It's a comedy, which was used as an uplink antenna for the Apollo program. So this is how the Jodrell Bank telescope looked. And this is how the Green Bank Observatory looks now. So these are all very sophisticated telescopes. So there are two sources of radio emissions. One is a thermal emission, which comes from temperature of a body. And all bodies emit radio waves at all temperatures. So this is an important thing for radio astronomers, because you can look at objects at any temperature and get information. But they don't emit light at all temperatures, only when they're heated to a few thousand degrees centigrade. And then the synchrotron radiation, which Jansky found, is it happens when electrons spiral around magnetic field. Now, electrons are plenty in the universe, and so are magnetic fields. So once again, this is a great source of information for radio astronomers. So the biggest problem at that time in the 60s was to find evidence for Big Bang. People thought that this was correct. The competing theory was the steady state theory propounded by Fred Hoyle. But there was no convincing evidence that the Big Bang was correct. And everybody was looking for evidence for the Big Bang. And Swaroop also wanted to find evidence. In fact, he was preoccupied with the problem. So the state of TIFR in the 1960s, when in 1963, scientists had just moved into a new building by the sea, next to the naval headquarters, the naval quarters, sorry. It's been a year, and the intellectual climate there was incredible. It had central air conditioning, which is unimaginable in an Indian scientific institution at that time, or probably any institution. Baba wanted scientists to work in comfort, and the campus was fantastic by the sea. People could go for walks after lunch. The gardens with a lot of interesting plants and animals, birds. So this is what Mumford described. I have got this in the book. The intellectual stimulation was intense. But David Mumford was a mathematician who worked in TIFR in the 1960s. He was a field medalist. The intellectual stimulation was intense. It felt as though half the world's algebraic geometers were there, and the other half came through for a visit. It was a highly interactive place. We talked continuously over lunch in the cafeteria, tea and coffee breaks, walks in the lush gardens and amid the astonishing hoopers and colored parrots. So even Mumford, who came from an incredible place, found TIFR to be an incredible place. But there were problems. So this is how India was in the 1960s. High ambition, but low in resources. For science, this was a big problem. Most of the scientists who had made a mark in the 20s, 30s were theorists. Bhatnagar was not a theorist. C.V. Raman was not a theorist, but science had been moving on since then, and it began to be equipment driven after the World War. So India did not have the infrastructure to do experimental science at the cutting edge. Foreign exchange was very scarce. What this meant was you cannot travel, you cannot import equipment, you cannot subscribe to too many journals. You cannot subscribe, journals cannot come by air, and they came by sea. So they came very, very late. So you're essentially out of touch and had no equipment. This was and no high-tech industry. That was because you need a private industry to make equipment. And if you want to make them in India, if you can't import them anyway. But if you want to make them in India, you have to get components. And there were no companies who made the components. So because of all this, most institutions did not work at the cutting edge. So this was the situation that Swaroop found himself in. And this is the opening paragraph of my book. I've just read it. Clouds had been, it was April 10th, 1960. Clouds had been gathering slowly since morning. The wind picked up through the day, signaling a turn in the weather. Govind Swaroop sat in the library of TIFR, watching the sea glittering in the intermittent sun, worrying about his future. Swaroop had moved from Stanford University to TIFR 2 months earlier, but he was yet to start work. He had no ideas. And he had been thinking about this for 2 months, but he didn't know what to do. Because he had some antennas, the antennas that Australia gave, they finally made their way to Delhi. And from Delhi, they came to TIFR. But that was not good enough for him to look for evidence for the Big Bang. And this is a problem that Swaroop was preoccupied with at that time. And he really didn't know what to do. And he describes this period, that take 2 months, as one of his lowest points. Because he had come back, he had given up a job at Stanford, and he didn't know what to do. So he had actually gone to the library. This was in the library to read some papers, but he did not read for a while. He kept brooding, and then finally he read 2 papers. So Nature had, on March 16th, had published 4 papers on radio astronomy. Swaroop found them on April 10th. There were 2 papers here. This was by Martin Schmidt, the first one, announced the discovery of quasars, large objects which with a black hole at the center. Some of them shone with the brightness of the entire galaxy, more than the 100 billion stars in the Milky Way, for example. And one other paper which Swaroop saw and got interested in was a paper which investigated this quasar using lunar occultation, using the moon edges to improve the resolution of a telescope. So when he read that, he immediately realized what he could do. So he could build a telescope that used lunar occultation to improve the resolution so that he could look far into the distance, into the early period when the universe was formed. So he thought that if you looked far enough, you would find how the universe looked like in the early universe, soon after its formation. And that would give clues to whether the Big Bang really happened or not. If the galaxies were close to each other, that means the universe was different 10 billion years ago, which was what people thought at that time the Big Bang happened. We know it's more than 10 billion years, it's about 13.7. So then Swaroop sat there and conceived of a telescope. We have seen earlier that the biggest telescope at that time was the Greenback Observatory, so 90 meters. He thought he would build a telescope just 530 meters long and 30 meters wide, more than half a kilometer long. And he would put it on a slope that is parallel to the Earth's axis. And then he would steer the telescope across the sky to track an object as it rose from in the east and went across to the west. He went to Baba and asked him, told him about his idea and said he will write a proposal. And then Baba said, don't waste your time, form a team and then we will see. And if once you form a team, we will fund. And the budget was around 58 lakh. So this was the challenge. If you build a telescope which is more than half a kilometer, it would weigh at least 200 tons, and it turned out to be more than 200 tons later. There were 24 dishes, each one of them separate, and they have to be steered separately, joined by 1,110 wires of 1 millimeter thickness. And these pieces have to be steered to precision of accuracy of a few millimeters. Nobody has that kind of accuracy in India. And in fact, the company which took up the project said we are used to in accuracies in feet, in tens of centimeters and not in millimeters. So he formed a team. Tata Consulting engineers got the design. They were not very keen to do this design initially because they were scared. They had not done anything before this, like this before. So then Baba had to convince them that if Baba will take the responsibility of failures if they put their best people on the job. Bridge and roof in Calcutta with the fabrication. Allenbury Works also from Calcutta with the gear system. And there were only two experienced scientists, experienced astronomers, MBG Sharma and MN Joshi from National Physical Laboratory in Delhi. They joined his team, and all the rest was students. The students built the electronics. Software was built by one of his students, C.R. Subramania. And he developed the deconvolution algorithms, which is when you to reconstruct the image objects from the image. So this is how it looks like. In 1970, the telescope came up. Soon after, on the day India invaded Bangladesh, the telescope collapsed. Part of the telescope collapsed. And it took another year for them to get it up and running. And they lost 1 year. But finally, it started operating. And it has been operating ever since. A picture like this does not give give any idea of how the telescope really looks like. If you go there, you realize how big it is. Its size is really extraordinary. So his aim was to find evidence for the Big Bang. The telescope was ready in 1970, but evidence for the Big Bang was found in 65. When Arno Penzias and Robert Wilson from Bell Laboratories found cosmic background radiation. But Swaroop and a first student Kapahi, who later became the director of NCRA, found additional evidence because they found that the galaxies were very close together soon after the universe was formed. And that paper was published in 1976. And since then, the UT telescope have been used for a lot of work and to study pulsars, used to study space weather especially. But then Swaroop had another big problem in his mind at that time. So to find hydrogen pancakes. So people thought that galaxies were formed from top down. There were huge hydrogen clouds which broke to form galaxies, which broke to form clusters, galactic clusters, and then broke to form galaxies from them, stars, and like. So he could not find them with the UT telescope. And he thought that if he built a big enough telescope, a much bigger one, he could find them. So he conceives an giant equatorial telescope to be located somewhere in the equator with a series of dishes that be big enough to find hydrogen pancakes. And he spent several years trying to find a location. He went to Kenya, he went to Indonesia. When he went to Kenya, he was supposed to meet Kenyatta, the president of Kenya, but the day after he arrived, Kenyatta died and he had to come back. And then this idea died. And Swaroop kept thinking about the problem for several years. And finally, on one night on New Year's Eve, late in the night at about 1 p.m., he got the idea that he would build a telescope like GMRT, which consists of 30 dishes about 45 meters in diameter, and together they would be able to look far into the universe and have a good resolution. So Swaroop moved to Pune to build the telescope. Pune was picked as a location. I mean, a village near Pune, about 60 kilometers from Pune, called Khodad, on the Nashik highway. Pune-Nashik highway was chosen as the spot after a long survey that took about a year. They went all around the country. They went to Indore. South India was not a good location. So they wanted to be north, to move away from the equator. So, and then the NCRA was formed under TIFR because this was near Pune. It was decided to form Pune headquarters. The telescope was ready in 2001. And now GMRT it's a low frequency telescope. And right from the beginning, about 30 countries use the telescope. And nobody could get a project automatically. Even Govind Swaroop could not get. It is still the world's most powerful low frequency telescope. So from GMRT, even as the GMRT was being built, Swaroop thought about an even bigger telescope. Hundreds of dishes spread, at 1-2 places on the Earth, far away from each other, so that you can get a long baseline. So that idea, there were others also who thought in those terms. It became the Square Kilometre Array, which is now a project with about 9 to 10 countries. India is one of the members who was involved right from the beginning in the negotiations. There were one set of dishes are in Australia, the other set of dishes are in South Africa. It's one of the biggest scientific projects the world has done. It has the ability to survey the sky 10,000 times faster than any other telescope so far. And India would never have joined this project except for GMRT and the experience gained from GMRT. So the amount of data that the SKA would generate is close to the total internet traffic in the entire globe. Up to 1 terabyte of data per second it will generate. And this is the biggest challenge for the telescope, to analyze this data. So looking back, Swaroop did not create just 2 telescopes. He formed an entire team. He formed a field in the country. Before he moved to India, there was no radio astronomy in India. Nobody had built a telescope. Nobody had seen a telescope. So now India is one of the leading nations in radio astronomy, with 2 big telescopes and a large team of astronomers. Why was he successful? And if you look back, there are not that many scientists who created an entire field in the country. So he was a very dominant personality who took ownership of the project. Now this has a flip side as well. There are people who say that he micromanaged, but in those days, because they were all young engineers who had not seen a telescope, who had not done anything, he had to take ownership, and he did everything. He studied engineering from textbooks. He was a physicist actually, not an engineer. but he studied engineering. He went through the accounts, managed the finance. He got people to meet the vendors and taught them how to talk to the vendors, not to let them cheat. Worked with the private companies, checked everything. And he would never let anything go unless he was completely satisfied. And he had a ability to look around him and learn lessons for scientific projects. So this would mean that he would, these lessons he would take from the novels of Premchand, which he read as a child, to what he saw around him in Takurdwara, how people made baskets, how they gave curvature to baskets, an idea that he used in giving curvature to Jayamati, the dish in Jayamati. And he had a doggedness. He would pursue an idea till the end, no matter what. And I'm sure many people would have these qualities. In those years, those were, so B.V. Srikantan created X-ray astronomy in India. C.N.R. Rao similarly created solid-state chemistry. M.M. Sharma created, we didn't create chemical engineering, but was a major figure at chemical engineering, who grew the field. G.N. Ramachandran was responsible for structural biology. So these were the people who built science early after independence, but for them, Indian scientific infrastructure wouldn't be like this. What is the relevance of these people to contemporary science? So they had a fierce motivation to build science in independent India. They lived through the independence movement and they experienced it. It is one thing to experience the independence movement and another thing to read about it from textbooks or other books. So they were all nationalists in a good way. They wanted to build a new country and they believed that science was important. And they all had an ability to work in a resource-constrained environment. Once again, this is a double-edged thing. Not everything can be built in a resource-constrained environment. Some things need money, but certain things don't. And they thought about what they could do. And they selected problems very carefully, things that they could solve, yet were important. Now, they had a willingness to convince policymakers about the need to fund science. All of them, Swaroop, C.N.R. Rao, M.M. Sharma, they were all networked very closely with policymakers in Delhi and relentlessly pursued science. So from an Indian context now, we are sort of at a stage where we will always be constrained, resource constrained. Money may not be enough. So we can probably take lessons from what they did. That's what I have to say. Thank you. I think I finished a bit early.
So maybe we could
stop screen sharing. Yeah. So Sushila, can I go first? Okay. So Hari, thanks for that. That talk. In one of your concluding slides as well, you point out other stalwarts like Professor Srikantan, Professor C.N.R. Rao, Professor Sharma, and others. What, in your opinion, are the lessons that we can learn from the way these stalwarts actually built institutions? I mean, every one of them is a legend in some shape and form, right? So what can we, in your opinion, and you've, I think in the course of writing your book, you've met them and interviewed them at length or interviewed their colleagues as well. What would you say would be lessons that today's scientists in all these institutions can learn from and build our scientific base?
They all learned how to work with very little resources. That was the first. I mean, we are always in a resource constrained environment. There will never be enough money for science. So there is no technique as such, in the sense it's not a methodology, like as they say, Jugaad or something, but they knew how to get things done. When you build an equipment, they figured out how to find the parts easily. They chose problems that they could do, are yet important. That is one. And the situation at that time was, country, they all had a drive, which was because they lived in a newly independent country. So we don't have that kind of atmosphere now in the country. We have 70 years for most young people. It's just something that you read about. I'm not sure, we can get the same spirit at this moment. When they all had good jobs, but they came back because they thought science was important. And over a period of time, this sense, and people believed science was important at that time. Now that sort of belief is gone away from the public perception at this point. Science is a bit distant. At that time, science was not distant. So science is
a bit what?
Science is a bit distant from the public. It was not so in those times. I mean, at least those who were educated, who read newspapers and who read. So it is probably a function of the times that they did well. Also, it is, we cannot transpose what they did to the current context completely, because we are now judged. We are not building a foundation anymore. We have to compete globally. So we cannot choose problems that can be solved. We have to do problems that have to be solved. Right? So find a way.
So would you advocate more investment in basic sciences if you are talking to policymakers?
Yes. It all depends. It's all relative. What is basic science? I don't know whether there is such clear divisions between basic science and applied science. Some of these projects, SKA that we mentioned, and the other big projects that India is part of, international projects, a fusion project, ITER in France, the LIGO, India's own, the TMT, the optical telescope in Hawaii. All of them are big projects, and they involve a lot of engineering. And science pushes the frontiers of engineering. So because if you're tackling a scientific problem, very often you would find that you would need an instrument that has never been built. Because a lot of scientific problems require instruments that don't exist. So when you build them, you build capabilities in many different areas of technology. So each of these areas can develop into full industry at some point. Sometimes they don't, but sometimes they do. So investing in fundamental science in many ways is actually investing in technology, in applied science.
True. So I know, when you write a book, you probably are constrained by, how much you can write. And, it also can't be a 1,000-pager. And so you miss out many things. But just to kind of ask you your opinions on a few things, like Professor MG Menon, also a stalwart.
Yeah.
What's your, have you researched him at all during the course of your?
Yes.
Do you have any comments that you can make?
Yes, he was an important part. He was Baba's deputy. And for Swaroop himself, when he came back, MG Menon made sure that he got all that he wanted. It was a very smooth transition. So even the equipment that he wanted to in TIFR were there when he came. But unfortunately, he had big ideas, and that equipment was not really enough for him to work with. But MG Menon supported big ideas, and after Baba died, he was the director of TIFR, and then later he went to Delhi and was a big figure in clearing big projects in the country. Without him, some of those big projects could not have been cleared, including GMRT.
And
but you can't write about everybody. This is not a history of
no, so, but since we are chatting about all these inspiring figures, you're looking at also people like Professor Satish Dhawan, or Dr. Vikram Sarabhai. I mean, these guys laid the foundations of institutions like the Indian Space Research Organization.
Yes. Well, the Foundation's Space Research Organization was done by Sarabhai, led by Sarabhai. And Baba also had a role in it because Sarabhai, it was part of the Atomic Energy Commission when it began.
Easy.
And Satish Dhawan came later when Sarabhai died. But he had a role because he smoothened everything, and he is very good in administration. He put procedures and made it a well-functioning machine, and he made it an open organization also. It's not that it was not open in the beginning; it was, but then he had instituted the system of reviews where anybody could ask anything. There were no hierarchies. Even the junior-most person could ask any question. So that culture remained in ISRO for a very, very long time. And Satish Dhawan had his role in building Indian Institute of Science is not that well known, but it was he who transferred Indian Institute of Science. He hired a lot of people. I heard that he hired about 60 to 70 people in 1 year. Went around the world, met young scientists and offered them jobs, made them come back. And he grew the institute from a small institution to a big institution. And he was handling, soon after that, he was handling space and IISc at the same time. And of course, slowly over a period of time, I think his attention was more focused on space.
So during your research, so there's an interesting question from somebody here. It says, why is the current scientific environment, why are they focusing on radio astronomy rather than optical astronomy? Okay. I don't think anyone's looking for a technical answer, but
I understand. Yeah. So in radio astronomy, so the earlier comment that they try to do what they could do rather than what they can, tackle the biggest problems that they could not do. So optical astronomy requires a lot of investment, much more than what India could afford at that time. And even in radio astronomy, they stuck to low frequencies where you don't need to cool the equipment to very, very low temperatures. You could work at normal temperatures. So even the UT telescope and GMRT are both low frequency telescopes. So, and they were built at a place where there was not much of radio noise at that time. So they selected the problem carefully. And this was an area where India could do something with that limited resources. So in optical astronomy, we still don't have a big telescope. I think the biggest is in Nainital. It's about 2.5 meters or something. I'm not sure exactly how much it is, somewhere between 2 and 3 meters. Well, around the world, people have gone more than 10 meters. So that requires an investment that was beyond the capability of India at that time and even now, and probably of most countries at this time. So that is why these joint global projects. PMT is an international project with many countries chipping in.
Also, I think with the Hubble and now the James Webb going up, you have better resolutions out there. So,
I think as far as I know, people have figured out a way to do optical astronomy from the Earth. They can match these space telescopes they have this technique, which is, which they use to compensate for the atmospheric effects, which will, give images which as good as what you can see from
Space.
Space, yeah.
There's a interesting question here that kind of is an extension of what you
It's called
mentioned.
adaptive optics, so I just couldn't get that word.
Adaptive optics, correct. There's a question here, something that you just talked about when you were in the context of Dr. Sarabhai. The question the person is asking here is vertical hierarchy to horizontal hierarchy in science. What are your suggestions?
I don't have an answer. Well, every horizontal hierarchy. I mean, I'm sure in most institutions are not that hierarchical. From a scientific point of view, people have the freedom to choose a problem, whatever they want to do. I don't think directors influence that much. It's a question of the ability to convince somebody that this project is important, and the ability to get funding more than anything else.
Sushila, you want to ask the others?
Yep, thank you. So here are a few questions on where does India stand with respect to other countries in the field of radio telescopy?
Well, India is one of the top nations now. I mean, if you say this is a very arbitrary list, but if you pick 5 countries in the world who do with a large radio astronomy community, who tackle the big problems in radio astronomy, we would pick India. Well, 30 countries, 50% of the proposals from GMRT is from outside India, and 30 countries use it. Now, I don't think there is any equipment in India which is used this way.
And what are in your research, what did you find are the important problems that people are looking at these days using the radio telescope?
So, as I said earlier, all objects at all temperatures give off radio waves. So this is a big thing for radio astronomers, because with optical telescope you can only look at bodies at high temperature, and with ultraviolet and X-rays, even higher temperatures. Of course, X-rays are very good at looking at objects that are very, very hot. But radio astronomy is good for objects that, for all objects, but especially for objects that are very cold. And so when the universe was born, after Big Bang, in about 400,000 years, I think it became transparent to radio waves. So since then, till the first stars formed, which we don't precisely know when that happened, maybe 500 million years, or 600 million years, sometime in between the birth of the universe till the first billion years, there was not enough light. In fact, there was no light in the beginning. There were only radio waves. So if you want to look back into the universe early in its evolution, you have only radio waves. So one big problem they want to understand is they call as a recombination. So at about 3000, when the temperature dropped to below 3000 degrees centigrade, the helium nuclei and hydrogen, the protons came to combine to form hydrogen and helium. So this era they call as the era of recombination. I don't know why it's called recombination, because it was only the first combination, but it's called recombination. So we don't know when precisely this happened. So getting signal for recombination is a big problem in radio astronomy. So similarly, when the stars formed and they began to radiate light and ultraviolet, because of this radiation, the gas became reionized. They once again become ions. the electrons were stripped off of the hydrogen atoms, and a lot of hydrogen became ionized hydrogen. Finding evidence for reionization is also a big problem. And you can use radio astronomy for many other things, for pulsars, because of this, the other thing, the synchrotron radiation, which happens when electrons spiral around a magnetic field. It gives a lot of information because there are a lot of the hydrogen is ionized, and there are lots of magnetic fields. So especially in pulsars, for example, they have intense magnetic fields. So radio waves are a good source of information about pulsars. In supernova, you can look backward after an event has happened, 10,000 years backward using radio waves, which you can't do with optical waves. And in many other big problems, radio waves are important.
Thank you. Someone wants to know, will the LIGO India come online sometime soon?
No. Well, it will come online, I suppose, but it will take a lot of time. Probably at 27, 28, around that time.
Look, let's come back a bit to what you were talking about earlier about the importance of science, and talk a little bit about that. You've won an award for the popularization of science. Can you tell us a little bit more about what you did and what can be done? What's your story?
Well, popularization of science is a word I'm not sure I like very much.
Okay.
Because I was telling stories, and it so happened that they were in science. I was a journalist. My aim was not to educate public about science, in the way science popularization is usually taken to be. My aim was to tell people about what's happening in the world of science and technology at that time. And I worked in business news publications all my life, in business world, first for about 18 years, and then Economic Times for another 7 years. So because of this accident, most of what I did was about private industry and not so much about fundamental science. I did write about science sometimes, whenever something big happened, like a Higgs boson or a gravitational wave and other things in health. But mostly I was interested in what private industry did, about R&D, about the biotech industry, about the pharma industry, about a little bit about IT industry. But I also wrote about space. Not so much about astronomy, but about the space program. So I was not trying to popularize science. It is a side effect rather than my main aim.
Sure. So, in terms of how premier educational institutions like the IITs, which is really the group of institutes that we have come together as alumni of, what can they do more to further science? And you talked about what happened when these greats of science set their mind to it and said science is important for this country, and indeed it is. And you talked a lot about all of that. How can we take it forward? What are some of your thoughts, and what have you, what would you like to suggest? And when you say science now, we're talking about, like you rightly said, you can't take out science and technology and separate them out. It's all kind of together. So when you put it like that, what are the directions? What are some of the actions that these institutes should be taking?
So most of the institutions, I think, doing the right thing, because Indian institutions have changed a lot in the last 20 years. The IITs themselves have become very, very prominent in research, which was not the case earlier. If you look at the output from Indian scientific institutions in the last 15 to 20 years, IITs have dominated especially in the last decade. That is because engineering as a subject itself has become important in research now, because there are a lot of publications. And that is overall good, because you can have the synergy between science and engineering. What has actually declined is this tradition of building equipment. So all this equipment that people built, not just 2 radio telescopes, C.N.R. Rao built a lot of equipment. Using very ingenious methods. I mean, methods means not a specific methodology. They found a way to build equipment that they wanted with very little money and using spare parts and this. So this has been a tradition, and I just mentioned one person, C.N.R. Rao, but several people in the 60s and 70s built a lot of equipment. At a time when there was not much support, there was no private industry, you can't get components that easily. But now that tradition has sort of declined. And I don't know why. I mean, I have not investigated too much. Probably it isn't possible. People tend to buy equipment off the shelf. But scientific instrumentation is still alive around the world. An example is, this cryo EM, electron microscope, which was built in Cambridge over the 15 years of work. So it is important for India to build equipment at the frontiers. There is some support from private industry now. We have capabilities, and this is the time to build equipment. And that is one thing that is missing.
Thank you. Ashok, would you like to? You need to unmute, Ashok.
So, so going into the realm of a little bit of speculation, there's a question here which says, will Musk's Starlink fleets likely interfere with radio telescopes? What is your take?
I have no idea.
This guy's going to put up some 10,000 of those little satellites.
So a lot of things interfere with radio telescopes now. And mobile phones too. The biggest problem is mobile phone. And sometimes TV broadcasts too. But I think they're aware of that. Radio astronomers have figured out ways to counter those. They're very clever. They know how to get data from that noise. But probably there is a limit to that.
Yeah, there will be, yeah. Because I think in the next 10 years, you'll probably see 50,000 little satellites up there, between all these guys wanting to offer you space-based internet services. So
it depends on what frequency they use.
Yeah, that's true. But
other frequencies will be, but there is a lot of noise, even in otherwise.
And a lot of junk.
Yeah, in Kodad, where it was a sort of a pristine place from a radio noise free. Now there is a lot of radio noise, but the techniques have also improved. They know how to handle noise much better now.
So we'll have to actually figure out the signal in the noise. So
yeah. So radio waves are so feeble. It's unbelievably feeble. If you put a mobile phone on the moon, the signals from that mobile phone would be stronger than from a radio object, an object in the universe. They are that weak, sort of a billion times weaker than a mobile phone signal.
There's also, I think, one of the questions here that there's a big telescope being built in Mauritius, and I think it is built with the help of Indian scientists. Are you familiar with that?
No, I'm not.
Yeah.
Right. Is it? No, I'm not.
Yeah.
South Africa is SK. India is part of that. They supposed to be part of that.
in South Africa.
South Africa.
Yeah.
Mauritius Telecom, I'm not.
Yeah. Last, I think, and this guy is an anonymous attendee. Okay. So he says, has politics in the scientific community decreased, increased, or remained the same in the last 1 century? I think 1 century is a bit too far. I mean, even if
politics is also a big word, because when you say politics, what do we mean? People remain the same, right? People have ambitions, people have jealousies. So human beings have not changed their character in the last 100 years.
Has not changed in your opinion?
No, human beings have not changed their character. So there are ambitions, there are jealousies involved.
Okay, it was a
So
very
there is some amount of politics in every, amount of politics in every institution, in every company. So I don't think, you know, scientific institutions are also free from that. But largely, this situation that now is politics from a different level. You know, this idea that what India should do, what India should not do. Things that come from ideologies. Then I'm not talking about any specific ideology. You know, the things like these are problems for the common man. So we should do such problems more than, you know, high science. So that sort of ideas is a bit that has more impact on what the future of Indian science than you know, small politics. So that is sort of an ideology. And this is not probably a political ideology to separate science into what is necessary for a poor country and what a rich country can do. I don't see science separated this way. Science is all one uniform thing. Either you do everything or you don't do it.
This you might find this a little difficult. You know, Professor Mishra is asking, signal processing plays a very important role in radio telescopy.
Yeah.
So do you know in your research, would you have met the guys who are the top dogs in this field?
Well, I don't know. A lot of the electronics for GMRT was led by this current director, Yashwant Gupta. He has, you know, who specifically did what, I don't know. Okay. And in Uti, C.R. Subramania was the person, and he's now still there, although he's retired and lives away from Bangalore. He is involved in this upgrade.
All right, so I think we are done. Sushila, do you want to wrap up?
Sure, thank you.
Yeah.
So we've had an absolutely fascinating peep into history, into the history of science in our country today. You know, when we got our independence, there had already been an environment of science and some wonderful scientists who had achieved a lot, including C.V. Raman, Saha, S.S. Bhatnagar, Homi Bhabha, and others. So that's where we started, but all of them saw the importance of science and the development of science for an independent nation that was getting onto its feet. And we looked at today, Hari talked us through the kinds of investments that went into science during that period. So we heard the story of Govind Swaroop, of how as a scientist who was in the US at Stanford and then came down to join TFR in 1963, how he kind of battled with what do I do with myself and what where should I focus? And eventually deciding that what was important for astronomy was to build a good radio telescope because of the need to set up something really impactful. And Hari has also talked us through today about how that step of setting up a completely indigenous radio telescope has been so important, not just from the astronomy point of view, from radio astronomy point of view, but also the development of many other allied pieces of knowledge. And why is this important? Why is radio astronomy important? This helps us despite the fact that radio waves are so feeble, they're still probably our best source of being able to understand questions like, why is our universe what it is today? How did it come to be? And these are questions that man has searched for thousands of years. So and this is only possible when you have the right kind of radio telescopes. So after Govind Swaroop set up the first, the GMRT, and the GMRT has been used by over 30 countries to help solve various problems, research problems that they've been involved in. And it's probably one of the best low frequency telescopes still anywhere in the world. And then he talked to us about the square kilometer array now, and India's role in both the concept and the building of that whole equipment. And this is across 2 parts of the world, and it's a wonderful example of what global collaboration can do. So last year when we had our IIT industry conclave, one repeated theme that came up was the importance of collaboration, of interdisciplinary work. And here is yet another great example of why and how that can be done. What is very clear is that when we set our minds to it and decide that we're going to do something like this, whether it is at the level of across institutions within India or globally, we do it, and we do achieve some wonderful results. And Hari wrapped up his presentation by talking about some of the characteristics of the scientists that he has studied for his book. And some of them are the motivation and the sheer determination to see that science would build out in independent India, being able to work in a resource-constrained environment, which we will always be, like he pointed out, but also the ability to to choose problems that were important to India, but solvable. And he also mentioned that going forward, the focus is less on the solvability than on problems that are important and at the cutting edge. And finally, he said that one of the key characteristics was that they had the ability to convince policymakers about the need to invest in science. And when you talk about a figure like 58 lakhs to build out a telescope in the 60s, that was a huge sum. And to have been able to convince Dr. Baba to do something like that would have, I'm sure, taken a good bit of doing. But we are also thankful and happy that they had that skill with them. He also, a few other observations. There is no more a clear demarcation between what is pure and applied science, and all of this is going to be important for us going forward. He also points out that one of the areas that India needs to focus on is equipments, building out equipments and instrumentation, because they are not just important from the point of view of scientific discovery or investigation, but also from the fact that they lead to many other skills and many other discoveries. And some of these technologies that are developed can also be applied in many other spaces. So Hari, all that remains is to thank you for this wonderful session. Thank you for being with us. This was a very different kind of presentation from the ones that we've done so far. And we really appreciate your taking time to be with us. To our audience, thank you for participating and being with us. Please look for the next edition sometime soon. So thank you very much.